Hi guys, I'm the data center dude.
And in this episode, I'm going to cover multi-mode fiber distances. We're all trying to get as much out of our fiber as possible, and with the addition of a couple new specifications, it's totally a good time to review what the best options are as you design or implement more fiber into your data center. I think most of us are familiar with the top part of this chart, but let's review. Starting at the top, the biggest difference between OM1 and OM2 is the core size. OM2 was the beginning of using the 50 micron standard from the previous core size of 62.5 microns. Although we changed the core diameter, we never changed the color. Both OM1 and OM2 are standardized as orange in color. What core reduction did for us back in the day was double the distance of our 1 and 10 gig links. They still weren't going very far, but 550 meters is a lot further than 275. The next big advancement in multi-mode fiber came in the form of OM3 laser-optimized fiber. We could easily spend way too much time discussing what laser-optimized is. In short, it's a 50 micron core solution engineered to take advantage of the 10 gigabit speeds from the new vertical cavity surface emitting lasers, VCELs, which replace the previous light sources called light emitting diodes or LEDs. LEDs were adequate for slower speeds. Utilizing laser-optimized OM3 in the data center
Increased distances of 10 gigs from around
80 meters to 300 meters, and so we began to see more data centers utilizing more multi-mode fiber runs in their architecture. OM3 was also easier to identify, standardizing in an aqua color. Again, we didn't change colors when OM4 was standardized in 2009. The major difference between the two laser-optimized fibers is in its bandwidth. With a jump in bandwidth from 2,500 MHz to 4,700 MHz translating into, yeah, you guessed it, longer distances. Utilizing OM4 technology, 10 gig is now going distances beyond 400 meters, and has been reported to reach over 500 meters on high-quality fiber. It also means you can transmit more information. For the first time, 40 and 100 gig optics can push at what we consider effective distances, 125 to 150 meters, suitable for most of your data center needs. This is probably where some of us get confused. There are solutions for us beyond what most people believe is the data center standard of OM4 today. With the increasing demand for 40 and 100 gig transmission speeds, more data centers are choosing OM4 Plus performance for better bandwidth and link distances. OM4 Plus features an advancement of effective modal bandwidth at 850 nanometers of 4,900 MHz or more and attenuation of 3 decibels per kilometer. That means we're now able to push our 40 and 100 gig signals out to 300 meters. As a bonus, although OM4 Plus isn't recognized yet by any optical fiber standards body, the industry has standardized on a violet color for OM4 Plus, which prevents confusion in the data center. Quite possibly the most confusion lies in our next standard, the lime green OM5. When you look back at our distance chart, it doesn't look like OM5 has any advantages over OM4, except the cool lime color, of course. But that's because OM5 was developed to support a specific technology, short wavelength division multiplexing from 840 nanometers to 953 nanometers. In short, this technology reduces fiber count by at least a factor of 4, allowing continued use of just 2 fibers rather than 8 for transmitting 40 and 100 gigabits per second in short-range applications. OM5 increases distances 50% over OM4 for customers using SWDM technology. This is because OM5 includes additional specifications of effective modal bandwidth and attenuation at 953 nanometers. To simplify, if you're utilizing 40 or 100 gig SWDMs, OM5 might be a solution for you. If not, go with the more affordable options in OM3 and OM4. Well, I hope this helped. Understanding distances and the new options is one of the most important and overlooked aspects of implementing new technology into your data center. Of course, there are other important aspects of actually ordering a cable, like the quality of the connectors or the actual fiber manufacturer being used. We'll totally discuss those in a future episode, so don't forget to click subscribe and the bell icon so we can let you know about new episodes. Later, skaters.
We love approved networks. We love approved networks for all your SFPs. Approved networks, guaranteed quality.
If you've never seen one of these before, it plays a key role in your internet life. This is what carries your email, videos, and games all around the world. It's an undersea internet cable. It's being made right here in Kitakyushu, Japan, at NEC's OCC factory. OCC makes submarine cables, which carry virtually all internet data across oceans. The cables come in different varieties, including heavily armored ones, but they all start with bundles of optical fibers. The fibers are wrapped in layers for strength, starting with a steel tube, then steel wires and a copper tube, and finally a polyethylene sheath for water resistance. Enormous spinner machines and spools are needed to create the cables. When they're armored, the cables are wrapped in more steel wires and then asphalt and plastic strings. That makes them pretty tough.
Even though the single armor is just one layer, this is kind of difficult to bend.
Once manufacturing is complete, the cables are spooled into large tanks and then tested for water resistance and other parameters. The cable system includes large missile-shaped repeaters to boost the signal across the ocean. This 9,000-kilometer long cable is being created for the Trans-Pacific Faster cable that's backed by Google.
It is a 6-fiber pair system. Each fiber pair will carry 100 wavelengths of 100 gigabits. So the total capacity will be around 60 terabits. That is equivalent to about 1,600 DVDs, which can be transmitted over the ocean in 1 second.
Once it's ready, the cable is sent out along rollers to a cable ship docked by the factory. This is the René Descartes, owned by French telecom firm Orange. Dozens of workers are needed to load the cable as well as the large repeater units onto the ship. Once inside, the cable is fed into 3 tanks below the main deck, and they're huge, hot, and humid. The cable has to be looped very carefully to prevent tangles. Back up on the main deck, we can see a few of the tools needed to lay the cable. About the size of a small house, the plow Elodie is used to dig trenches on the coastal seabed where the cable needs to be buried for protection from anchors and nets. Next up is the Hector 6, an ROV that can work up to 2,000 meters below the surface of the ocean. It has caterpillar tracks for propulsion, jets to help bury the cable in its trench, as well as robotic arms to manipulate it. On the bridge, engineers can control the arms with small-scale replicas, as well as joysticks to control the ROV and plow. It takes a light touch and a lot of patience to install a cable all the way across the Pacific. In Kitakyushu, Tim Horniak, IDG News Service.